All right, so section 4.6 again, number 26. All right, so didn't want to write this one out, so I took a picture of it. A fence 8 feet tall runs parallel to a tall building at a distance of 4 feet from the building. What is the length of the shortest ladder that will reach from the ground over the fence to the wall of the building? It's kind of an awkwardly written question, so I'll try to give you a sense of what's going on here. So this is not the best picture in the world, but hopefully it'll get you a sense. You can get a sense of what's going on by looking at it. So of course the big rectangle here is the building, and the small thing over here is supposed to be the fence. And I didn't put any third dimension in the picture for the building. It's going to crowd the picture a little more than I would like it to. So let's just try to understand what's going on. The building, moves in the third dimension into the screen, and the fence does as well, okay? So the key is that the fence, the length of the fence, how long it is irrelevant. Really what matters is how far away the fence is, how tall the fence is, and what we're trying to do here is we're trying to put a ladder from over here on the grass so that it hits the top of the fence and then ends up hitting the building. And I was a little short on that one here. So something like this, okay? So the ladder, again, the length of the wall, how far the wall goes back is irrelevant, okay? What matters here is the height, how far away from the building the wall is, length of the ladder, those types of things, okay? So imagine standing to the right of this wall, and you need to somehow get high up on this building, and you've got a ladder that you're going to use, sorry about the bell, and you want to figure out the length of the ladder needed to reach high up on the wall. I'm going to go back and read the problem, make sure I'm not missing anything. What is the length of the shortest ladder that will reach from ground over the fence to the wall? So just to make sure, the fence is 8 feet tall, so I got to go put that in there. So we have 8 feet over here, so I'm certainly not in proportion. There's 8 feet here, and there's 4 feet here. My wall and my lengths here are not in the right proportion. But nonetheless, this is how we need to approach the problem here. So the length of the ladder is an unknown, so let's add that to the picture here. So this is all x. That's what we're trying to figure out. We're trying to find the smallest value of x for which this would work. Now, obviously, the ladder is going to have to be more than 8 feet tall, or it's not going to even reach, over the wall. So it's going to be a longer than 8-foot ladder in order to be able to reach past the wall, over the wall, go over, 4 feet in that direction, and be up high on the building. So how are we going to set this up? So we're going to have to put some thought into the mathematical relationships that we need to figure this out. So pause the video, see if you can add some stuff to the picture, and figure out what's going on here. So let's try to abstract some math out of this. Let's take a look at this picture over here. I called the length of the... Oh, whoops. Using the wrong tool at the moment. I call the length of the ladder x, which stretches this whole length out here like this. We know this is 4 feet right here. We know this is 8 feet right here. And so if I call this something like y over here to complete this length, and call this like z over here, the height here, I can start setting up some mathematical relationships. Well, we have the Pythagorean theorem here. X squared is equal to z squared plus, I'm going to go back and make sure I got this right, y plus 4 squared. Quantity squared, like this. And we're trying to minimize x in this equation here. Now the issue with this at this point, again, is that we have 3 variables in here. So we have to figure out a way to reduce this down to just 2 variables. So I have to get rid of the z or get rid of the y so I can work this out. So if I go back over here, hopefully you see some other geometry in here. You see some similar triangles going on. So I can set up a proportion like let's see, how about 8 over y, the height of the small triangle to the base of the small triangle, is going to be equal to z, the height of the big triangle, over the base of the big triangle, 4 plus y, like this. And so from this, I could solve for z, let's say, and we get z is equal to 32. I'm going to go ahead and distribute now just due to space. 32 plus 8y. Whoops, doesn't even look like a y, so let me redo that. Over y, like this. And I can put that in place of z in my equation on the other page here. So x squared is going to be equal to something squared plus y plus 4 squared. What was that something again? Now I'm debating whether I don't want to leave it as a fraction or separate it. I think I'm going to separate it. We're going to have 32 y to the negative 1 plus 8. So let's just go back and double check that. Yeah, 32 over y is 32 times y to the negative 1, and then plus 8. So what do I have to do now? I have to figure out the domain of this equation here. Domain, all possible values of y that make sense in here. Now, see, why is this length here? Now, I think you probably see it up here that y can't be 0. If y is 0, then the ladder would be vertical, so it has to be something bigger than 0. So it's like this. So we're going to use our first derivative test for absolute extrema instead of the closed interval method. And then how big can y be? Well, theoretically, y can be as big as we need it to be. It could go on to infinity. There isn't anything restricting, except for maybe the Earth itself, and maybe you want to put the diameter of the Earth out there as a possible boundary. I don't feel like looking that up. So theoretically, let's suppose we're in a universe, Euclidean universe, where it could go on forever. Infinity would be fine. So now what do I need to do? Well, the first derivative test for absolute extrema. I need to take a derivative. Instead of taking a square root here, I'm just going to implicitly differentiate with respect to y, since y is my input variable. And I'd rather use that than trying to get a square root involved here. So if I implicitly differentiate, we're going to get 2x times x prime. I'm not differentiating with respect to x, I'm differentiating with respect to y, so I have an x prime there. And then 2, and I'm going to get 32y to the negative 1 plus 8, and then I'm going to multiply by the derivative of the inner, which is going to be negative 32y to the negative 2 plus 2y plus 4. And then luckily the derivative of the inner is just 1, so I'm not going to have to worry about that. I found a select and copy and thus paste feature. So I just copy that and paste it over to the next page so I have some space with which to work. All right, so we got to figure out where x prime is equal to 0, where x prime is undefined. And x prime is going to equal 0 if we have any division by 0, and that's where either y is equal to 0, as we can see from these expressions here, or ignoring those, when I actually go ahead and divide by 2x over here, I'd have to know when 2x is equal to 0. But 2x, x would be the square root of all of this mess right over here. That's never going to be equal to 0. Otherwise, we wouldn't have a ladder that we're dealing with. And so I don't have to worry about when x prime is undefined. Now x prime is going to equal 0 when just this stuff on the right-hand side is equal to 0. So that's the part I need to work with here. So we have some algebra to do. Let's go ahead and start distributing a little bit and see what we come up with. I'm going to turn this off so I'm not recording this and get the results. All right, so I got this mess here, and I'm starting to wonder if there was some algebraic issue that I've had along the way. Um, well, I'm going to pause and go look over my algebra. So I checked my algebra, everything looks to be fine, and I did a few extra steps here. So I combined everything into one single fraction, getting the common denominator of y cubed, which became this. This is equal to 0 when the numerator is equal to 0. And so I have the numerator equal to 0, and then I rearranged it, putting my highest exponent first, and then dividing everything by 2 also to have hopefully something a little bit easier to work with. So I think we got to factor this. I'm hoping that this factors in the way my mind is seeing it. So I'm going to factor this by grouping, which is something that you should have learned about at another time. So actually, let me not put those parentheses in. I'm going to group them into pairs like this. You did stuff like this in pre-cal. So in that first pair there, I could factor out a y cubed, and I'm left with y plus 4. And then in the second pair, I'm going to factor out a negative 256, which leaves me with y here and 4 here, because 4 times 256 is 1,024. And then that equals 0. And then I can factor out a y plus 4 from each of these terms here. I like how I said 4 and wrote 3. And then what I'm left with is y cubed minus 256 is my other factor, equals 0. And then by our zero product property, we're going to get y is equal to negative 4, which is not possible in our context that we're dealing with now. And then I get the cube root of 256, which I'm trying to think, 256 cube root. I don't think that works out to be a very nice number anyway. Okay, so let's go back and look at our domain really quickly. Oh yeah, it was 0 to infinity. So now I need to set up intervals from 0 to the cube root of 256. And then the cube root of 256 to infinity. And we're going to test values for this into x prime, which might be a little bit of a challenge because we never actually solved explicitly for x prime. But we'll work this out though. So let's see, cube root of 256. That's got to, 100's got to be over here. You could argue that one fairly quickly. So let's go back a little bit and let's use this equation here on top. The 2x that we have over here, I don't have to worry about that in the value of x prime. That's always going to be a positive number. And so, and that goes back because where we're getting x from, if we had x squared is equal to a mess. When we solve for x, we get a positive root for the length of the ladder. So that has to be positive. So we don't have to worry about that. It's all this other mess that we have to deal with, which is just this stuff down here. So I'm going to use all of this, and imagine if I plug in 1 for y. If I plug in 1 for y, then I get these really large negative numbers here and some small positive numbers. So we're going to get a negative number. So that's going to be less than 0. If I plug in 100, then 100 cubed, is going to be, what, a million. And then 100 squared is going to be 10,000. So these two terms are going to be really, really small but negative. And then 2 times 100 plus 8, it's going to be bigger than those. So we get a positive result, greater than 0. And so this tells us that because x prime is negative and then positive, always negative before cube root of 256, always positive after cube root of 256, means that we have a minimum length of the ladder at the cube root of 256 for the value of y. Now, what do we actually have to do with that? The question wants us to, what is the length of the shortest ladder? So we actually have to calculate the length of the ladder, which means you need to plug your value of y into this equation here, the cube root of 256 into this whole entire equation, and then solve for x, needing to take a square root. And that'll give you your final answer. I'll let you do the work on that one since I've done all this other work for you. I hope it was helpful. I hope it wasn't too confusing. Calculate well. Go study.